Okay. All right. Hello, everyone. I'm Alex Fan. I will be one of your instructors. Welcome to the first ever lecture of 6.SO88 Algorithmic Problem Solving. Thank you guys so much for coming, and very, very excited. Yeah. So today, no, we're not. Oh, actually, before that, we'll have our instructors. So huge shout out to all of these amazing people. They've been working all day, like during winter break. I know Richard here was preparing like a curriculum throughout winter break, really, really busy. So Wei-Ming Zhou, Balint Rosha, Eric Yang, Dylan Isaac, Thomas Liu, Alex Van, and Richard Xi. Thank you guys so much for your hard work, and we cannot wait to share this journey with you guys. So, what is the purpose of our class? There's really three broad categories of what we say like programming. When we have, the theory people, if you take in 6121, 6122, you've done a lot of like theory, you have like summary structures, you briefly know like the complexity of things and what things generally are. But I think there's a pretty big disconnect between that and the implementation. So if you go into, say, a code interview, I'm sure a lot of you have done leak code before in the past. Like, there's actually quite a big disconnect between what you've learned in class and actually being able to put it down in your editor, in code, and make it actually work as intended. So that's just like the other camp. And then finally, you kind of have the third group of people who are like the tryhards, the competitive programmers, like our own club. You grind on Codeforce, you go on like DMOJ, you go on AdCoder. And like, in a sense, it's also somewhat different from the other two camps. I guess kind of curious, like who here considers themselves as like theory people? Like you've taken 6121, you've not only tried like, implementation before. Yeah, raise your hands. Okay, we have like some people interested in like, if you want to like use this class as a launchpad to either do 6122 in the future, 6.854, I believe, advanced algorithms. Like I think you'll learn something from this. Who here is like interested in the leak code or like the job interviews, coding interviews? All right, we have some people here. Very nice. And then finally, who here is like try hard nerds, trying to get into competitive programming, become a grandmaster on Codeforce? Like who here is, I guess. Oh, nice. Okay, we have a couple tryhards. Love to see that. If you want to join our club, MIT Informatics Tournament, we'd love to have you. Cool. All right. So, kind of more logistics on our class. With the format, we are a somewhat intensive class, as in we have lectures basically every day for this week and the following week. The format-wise, we have lectures from 4 to 5 p.m. every day. This is where we kind of go over concepts. We generally are going to be more like theory-based. We show some examples. We'll do some live coding, but in general, it's more kind of like going over the concepts first. After that, we'll have a problem-solving session from 5 to 7 p.m. This is where the good things happen. You actually get to code stuff. You get to talk to our TAs one-on-one. And this is where our pizzas and our dinners will happen. So I'm sure you guys are excited for that. And then some topics that we're going to cover today. We're just going to kind of go over logistics and get our feet a little bit wet. We're going to go over a really, really hard problem called binary search. I know, very riveting. And then we'll also go over what could binary search look like if you are a tryhard. So kind of get both a flavor for beginners and also for advanced people. And then the following day, we'll talk about range queries. From the basics like prefix sums that you might encounter in like leak code. We'll also go over more advanced concepts like segment trees, intervals, lazy propagation, and really having these like really rich set of operations that you can like do on ranges. After that, we'll do trees. We'll start from the basics. What is a tree? Is it things you touch? No, it is a set of vertices and edges. And we'll talk about LCA. We'll talk about diameters. And for our advanced lectures, we'll go into heavy light decomposition. This is one of the most advanced, or like my favorite decomposition for trees. And you can do a lot of really, really cool operations on them once you know what they are. After that, we'll go into DSU. So the swing set union, really powerful data structure, very simple. You kind of keep track of pointers and somehow you just be able to tell if things are connected. But there's actually a lot of really hard things, even within DSU itself. Like, I'm not sure how many people know the inverse Ackermann complexity analysis for DSU. It's insanely hard. I honestly forgot everything already, so we'll dive a little bit into that. And for advanced, we'll try to solve the offline dynamic connectivity problem, which is one of like the big things you can do. You can also deal with a display tree, but I think the fact that you can do it with DSU by itself is also really cool. And finally, we will dive into our DP unit. For beginner, we're just going to go over like memoization. We'll go over some basics, like knapsack problems, etc. And then for our advanced unit, we'll go over more cool things like profile DP. We'll go over bit mask. We'll go over like really weird things that you won't even think it's DP, but it actually is DP. In some sense, this is like one of the most common topics that come up in code interviews. So I think it's a really cool unit if you are interested in that. And finally, for our last day, it's kind of like a free-for-all. We call Fun with Ad Hoc, brought to you by Thomas. This is like topics that are really cute. They're self-contained. You don't really have a specific technique you use to solve them, but they have like these random observations or like weird tricks like, you notice that it's always divisible by 10. And if you like do every other operation, somehow like everything magically works out. Things like that. You don't know why they work. They're magic. They're really fun. That's going to be our last day. After this, we are going to begin our MIT Informatics tournament. I encourage everyone here to participate. It's like a really nice way to sum up your like journey here. We have mini activities on the 18th, which is the Saturday following. We have like poker tournaments, like karaoke, whatever. It's like a nice way to socialize and meet other people. And finally, the following day, the 19th, we'll have our actual big tournament. And as you'll see, quickly over. For the languages, our class will mainly use C++ and Python. These are, I think, the more common languages used. However, if you like to use other languages like Java or even OCaml, Haskell, whatever, our judges should be able to support them. And also, we'll have really cool swags that we'll be giving out. For every problem you solve on our homework contest, you'll get a raffle ticket. And for every class you attend, you'll also get a raffle. In the end, we'll choose the top 10 lucky winners to win our exclusive limited edition MITIT poker cards. We are not a quant club, I promise, despite the allegations. Grading-wise, we are a 4-credit class, but it's pretty easy to pass. It's P and F. And you'll pass if you either solve a total of 5 problems on our contest platform, or if you simply just participate in our tournament at the end, you'll pass. So pretty simple. All right. Finally, we will have our other instructor, Richard Shi, go over binary search.
What's up? Thanks everyone for coming. First I'll give an intro, just like what like solving problems looks like for like people who haven't done that before we get into binary search. So what is like competitive programming? So like the reason we're like going with competitive programming is because like it's a nice way to learn algorithms and code at the same time. So like you'll be given a problem which is like an algorithms problem, and then you have to code up the solution to it. And we'll hopefully we'll help you out right after this lecture with like examples if you've never seen this before. So what the program does, it like takes in some numbers and it outputs some numbers. This is like pretty abstract, but that's essentially what it does. And then it also needs to be fast. So you can learn more about like other details here, but we'll get into an example first. So here, this is the interface that you guys will be using for the class. It'll look like a problem here, and then there'll be some text to the problem. So first thing you'll do, you just read the text. Zoom in a little bit. So here, here's a problem where Gordon Ramsay backwards is baking some cookies, and so he has n batches of cookies. Each batch has some number of cookies in it. And then he wants to share his cookies fairly with a friend. There's a lot of text, but essentially what it's saying is you need to select 2 batches of the cookies and then divide them evenly between 2 people. What that means is that you need to select 2 batches of cookies whose sum is even. And then you need to select another 2 batches of cookie whose sum is even, and then so on. And you do that as many times as possible. So here's an example. This is what an input looks like. So this 8 here means there's going to be 8 numbers. And then the 8 numbers down here are how many cookies are in each batch. So right here, what we can do is you can take the one batch of 1 cookie and the batch of 3 cookies, and that together makes 4 cookies, which is divisible by 2. Then we can get the group of 5, the group of 7, and that makes 12 cookies, which is also divisible by 2. We can't do something we can't get the one batch and then the 6th batch, because that makes 7 and then not divisible by 2. So yeah, the output here is like the maximum number of like times you can like group together these cookies. But it turns out it's 3 here. So yeah, generally you have to like kind of think about it for a while. Here I'll kind of speed through it. So like the idea here is like to get an even number of cookies, you need like 2 odds or 2 evens, and those are like the only possibilities. So if you look at all the odd numbers, we'll like put them into groups of 2, and then those will form even-sized groups. And we can also get like the even batches, so like 2, 4, 6, and then we'll like group the 2 and 4 together, though we can't do anything with the 6. And this is what it'll look like to implement something like that. So this is what you're saying about like input and output. What that means is like here's the input, so you copy that over. You can use like any sort of coding thing you want, and then you have like the integer n, which is like how many numbers there are, and then a is the array. So if you like print that back out, this is what it means when we say like input output. It's just like that, and we get the array back. And now back to actual problem. We want to do is like count the number of even-sized batches and number of odd-sized batches. So what we'll do is like go through the array. If it's even, then we'll increment our even number. Otherwise, if it's odd, we'll increment our odd. So, and then afterwards, we need to like group the evens into group sizes of 2, and then the odds also in group sizes of 2. So in Python, what that looks like is like you just divide each group size by 2 and sum them, and then you get their output. So then after you think it's correct, you'll go over here, and then there'll be a submit button here, and you paste it in. There's going to be like all sorts of languages, but like probably you'll be using Python or C++. Let me submit that, and hopefully it's right. It'll like run in a bunch of tests, and then okay, nice. So nice, and that's what it'll be like to solve a problem. This is kind of like a rushed version, but yeah, you'll get some hands-on practice later. Yeah. And for C++, like reading in the input, what we just did for Python is on the left. C++, it's a little bit longer, but basically the same principle. You just read in numbers and then output numbers. So for like analyzing runtime for what we just did, it was kind of simple because we just like looked at like our n numbers in the input, and then we like went through each one and like check whether it's even or odd. That's just like n operations. You can imagine if we have like a for loop inside a for loop that's like n squared. You've probably seen analysis of like, okay, if we have like 3 for loops, it's like n cubed, and it's kind of like notation that we use is just like if we have like some n cubed terms and some n squared terms, like we just look at the bigger ones. We'll give some examples later. And like basically this notation is just like what competitive programmers use like whenever we talk about solutions. We'll be like, oh, this is an n squared, not good enough. We need like an O of n. Yeah. And usually for like competitive programming problems, like you just like look at the complexity if you have like 2 for loops or something, and then it'll be like n squared. And you might have to adjust that a little bit based on like, because like you're running like actual computers on like actual code, and it's like actual time that you're measuring, so it might be like off by like some factors or something. But for most of the time, you just have to like kind of like estimate whether it would run in time, and you'll get some practice with this. So now to the mini lecture. So today, because we spent some time talking about like the intro and logistics, it'll be a little bit shorter. And also what we'll do here is like first have some portion which is like what a beginner lecture would typically look like, and then followed by what an advanced lecture would look like. So this starts like the beginner lecture. So binary search. You've probably like heard of it to some extent, but the way we like generally present it in competitive programming is like this one problem, which is like you have an array and there's a bunch of numbers in it, and then you want to find like the index, the first element, which is at least 8 in this example. So what is that here? Like 6 is not at least 8. Like 22 is too big, but like the 8 is like right there in the middle. And if we were to like just like search through the array, we like look at the 1, 1, 3, 5, 6, and then we like, oh, we get to an 8, and it's like, okay, that's at least 8, we're done. That takes like a lot of n time because like we have to like sort of scan through the array. If we imagine like, let's say like we want number at least 22, you have to go all the way through the entire array, and then you get to the last element. So it could take n operations.
Hello. Hello.
Oh. Hello? Oh, could you mute? Sorry. Could you ask questions in the Zoom chat? And then our staff will try to answer it over there. Okay. You guys good? Oh. Yeah, no, honestly, could you answer this question over Zoom? Or Don? So, sorry, to binary search on the array here, let's say we're looking for the first number, which is at least 8, the example we just showed. But like we don't want to do like what we just did, where we like looked at the entire array. Let's look at the middle element, and then like, okay, is it at least 8? It is at least 8. So, but we're not done yet. The reason we're not done is because we want to find like the first occurrence of 8. The first occurrence, which is at least 8. So like, it could still be like over to the left. It actually is to the left. But here, like, since we found something which is at least 8, we can ignore everything to the right. So what we do here is just like, the non-green part is like, we can just ignore that part of the array. And now we're like looking at this left half. And we're still looking for like a number which is at least 8. So we can look at the middle over here. Be like, okay, is that at least 8? It's not. So we can just ignore that element and then everything to the left, because like, it's not going to be at least 8. And we repeat that. And like eventually we get to like the first occurrence of 8. And if you notice here, like it's less operations.
There is no video on the Zoom. Can you go to
Oh, I see.
No.
Thanks. Does this entire screen work?
I don't think we know.
Alright.
Alright, nice.
Cool. Sorry about that. Yeah, so back to our like this example, like the number of times that we've like searched through the array or like picked out an element. Here it's not like O of n. Every time like we select an element, like that green portion that we're looking at like halves, and the number of times something like halves until it reaches like 1 element, that's like the number of times you need to divide a number by 2 in order to get to 1, and that's like log n, log base 2 of n to be precise. And so in competitive programming, we just denote that of like O of log n. Yeah. And okay, so like what we just did like on an array, like that's actually a really common like problem that people like end up needing to like kind of use as like a sub-function in their code. So like and then also sorting, there's like functions for that. So like typically when you get an array, it doesn't come sorted. So when you're looking through elements, you need to sort it first. That's what these two functions do in Python and C++. And then these you might not have seen, but these like kind of solve the problem that we just went over.
If you're speaking
Apologies for the technical difficulties.
Yeah. Sorry guys. So yeah, to like solve that problem that we just presented of like finding the first element which is at least something, let's like look at what it looks like in C++. That's that problem exactly is called like lower bound. This looks sort of complicated, but we can kind of skip over that. And like what it does is like find the first element in an array or something else, which is like at least x. And then what it does inside is it does this binary search that we just talked about. Yeah, I think that there's a lot of like names up here. You don't have to pay attention to this, but yeah, this is just a function that's already in the language that does a binary search. And now we'll go over like a simple example problem. So usually it won't be just like find the element in the array which is at least x. It'll be something a little bit harder than that, but like kind of uses that principle. Here's that problem. So we give an array of n integers, and then we want to find two values which sum to x. This is called like a two sum, and like how we would do that. Like without binary search or anything, is you would sorry, reading in the output here. So first you have like the number n, which is like how many elements in an array, and like the sum that we want. Here we want a sum of 8, so it'd be like 7 plus 1. And then the output here is like the second element is the 7, and the fourth element is the 1. So, okay, let's copy in this input. We'll also post this exact problem later in the practice session, so you guys can do this later. And then what we do with binary search is go through the array in 2 for loops, and then check if the sum is equal to what we want. And then if so, we print out. I guess we can do like otherwise print impossible. So yeah, if we find those two elements which make up sum, then we're good. And if not, then we need to print impossible. Let's see.
Let's split.
Oops. Yeah. That's wrong. Wait.
Plus 1.
That's
0
it.
x.
All right. Yeah, and we can print out any of the solutions. And if we try to submit this, actually, let's just try now. So there are 2 for loops here, so it'll be like n squared, and then what is Python? Py3 is like fast version of Python. Yeah. So while that's running, yeah. So this is like, if the problem were just that would be nice, but unfortunately it's a little bit harder. So let's see. Okay, so we'll go through the array and sort it, but if we just sorted it right away, then we would like kind of lose track of where the positions are, because at the end we need to print out the positions. So let's see, the simplest way to do this. So you can keep track of like the array with indices. So we like have the value and the index. Wait, let's check back on our submission here. So yeah, so you see time limit exceeded. What that means is like it was too slow, but it was like generally correct up besides that. So let's comment that. Okay, and now we'll sort our array. All right. I realize this example probably might be a little bit long. So in order to like find the element, okay, so we'll first like go through all the elements, and then, okay, and then look at the value for that index. So yeah, so we have like some value that was at some index, and then we need to like find the other element which makes it sum equal to like our desired sum. So we need to make a sum of capital sum. So then we need a value of like sum minus value. So we're like looking for this. So then like in our array with indices, we'll like look for the value. We're now looking for this value inside of the array. Okay, I guess in the interest of time, I'll like write out the pseudocode for this. So like we want to look for this value, but now we have like a sorted array, and we're like looking for this value. But like if we're just looking for a value in a sorted array, if you remember like what we just did, that was like finding the value which is at least something. We can like find the first value in the array which is at least this value, and then like check if it's actually that value. And then like if so, then we found our desired value, and those two things sum to the correct amount. Okay, but there's actually a small detail here, which is that like you might find the same value in the array as the value that we just had. Okay, as an example, like as an example here, like let's say there was a 4, and then we like looped through the array, and then we found a 4, and then we're like, okay, now we need like another 4 to sum to 8, and then we have like look for the next 4. Then like we might find like the same element again, and then there wouldn't actually be 2 values which sum to 8. So there is some details here. So I'll leave you guys to implement that in the practice problems. Yeah. All right. So that concludes like the beginner mini lecture, and now for like an advanced mini lecture. Okay. So like what we do with binary search of like looking for a value in an array which is at least something, that's like not actually typically where binary search is used. Usually it's used in something called like binary search and answer, where like binary search is kind of an ingredient in the problem, but then like there's this entire other part of the problem which you need to solve like using something different. So this will involve like some like BFS like concepts about graphs. So if you're like looking for beginner lectures, don't be intimidated. So yeah. So like this is our problem. We have like a graph, and it has like some number of nodes, some number of edges, and it's weighted. So like every edge has some weight on it, and then we're gonna be given like 2 nodes, and then we want to find like the shortest path from A to B. But shortest path is like not what you typically hear, where like normally like the length of the path is like the sum of the edge weights, but here we're looking for the kth largest edge weight, and we want that to be minimized. Okay, that's a little bit like hard to parse. So like if k is equal to 1, then we want to find a path such that like the maximum edge weight is minimized. And we'll go over some examples here. So let's look at this graph on the left. So the circles are like the nodes with like the number inside being their index, and then we're looking at a equals 1, and then like b equals 4. So we're going from 1 to 4, and then we want to find we want to minimize the kth largest edge weight. So k here is 2, which means like we want the second highest edge weight to be minimized. So example, if we go from 1 to 2 to 4, 1 to 2 to 4, like we cross like the 4 and the 5. But then the second largest edge weight there is like the 4. The 5 is like the largest. We could instead go from like 1 to 3 to 2 to 4, and then we would go through weight 2, weight 1, weight 5. So that's where we get 2, 1, 5. And then the second largest edge weight would be 2. And we can do this for a lot of the paths. So for this last thing here, we could go for like 1 to 3, back to 1. We could go to 3. We could even like go back a bunch of times. And then we can go to 2 and to 4. And then the edge weights that we would cross would be this 2, and then the 1, and then we can potentially like go back and forth. And then, but then like, no matter how many times we do that, we'll get like 2, 1, 2, and then like our last edge weight we cross will be a 5. So then the second largest edge weight will still be 2. And now like, if we look back at our like original problem statement, which I put at the top. So like we want to like minimize this this ending value that we get. In this case, the minimum possible value, there are these like bolded underlined things, is 2. Okay, so like to kind of like solve it directly, it's kind of hard to see. Like you can't do something like Dijkstra's because like you're not doing shortest path exactly. You have to like kind of think about it. And then what binary search like with answer tells you to do here is like, let's instead try to see like, is the value at least some amount. So let's say like, or okay, similarly like at most some amount. So let's check if the answer is at most 3. So how do we like check if the answer is at most 3? Well, we can like look at like all the values which are like less than 3, and we'll set them equal to 0. Because like if we're trying to check if the answer is like at least 3 or like less than 3, all that matters for weight is like, is it greater at least 3 or is it like less than 3? And everything less than 3 we'll just call 0. Everything at least 3 we'll call 1. And so that's how we get from like this graph over here to this graph over here. And now, after we've transformed that, we want to find whether the graph has like a path which has like kth largest edge weight equal to, in this case, like 0. What that means is like a 0 here corresponds to like the second largest edge weight being less than 3. So if you imagine, let's look at the same paths we were just looking at. So 1 to 3 to 2 to 4. In the original graph, it would be like 2, 1, 5. And the second largest edge weight would be 2. But now in this new graph over here, it'll be like 0, 0, 1. And then the second largest edge weight would be 0. And what it tells us is like the second largest edge weight is less than 3 in the original graph. Yeah, so basically like whenever we're checking whether the answer is at most something, we'll like use that value. Everything like at least that amount will be set to 1. Everything lower than that amount will be set to 0. And now we have like a 0, 1 graph. And then like 0, 1 graph is very like easy to analyze in that like now we just are looking at like the shortest path in terms of like the normal sense of the term. And the shortest path in this new graph is the 1 to 3 to 2 to 4. And then because like there's only a single 1 on that path, we know that there exists a path in the original graph where like the value is less than 3. So yeah, this kind of summarizes like the entire process here. So like instead of like directly trying to solve the problem with some algorithm, we want to check whether the answer is at most x. In that case, x was 3. And then we like use that value of x. All the edges which are smaller, we set to 0. All the edges which are like at least, we set to 1. And then we run like normal BFS through that. BFS finds like the shortest path in that like 0, 1 graph. And then looking at that path, we can determine whether the sum is at least greater than x or like at most x. And okay, so this is like kind of like an involved example. This is kind of what you'd expect for like the more difficult problems. You have like some outer layer of binary search. And essentially like what you're doing at like a higher level is like originally like you want to find an answer, and then let's say the answer is like a number. And then instead of finding the answer, let's just see like, is the answer at least y? And then maybe that's an easier problem. So like if that is an easier problem, and then you can solve that easier problem, what you can then do is like use that easier problem to solve the harder problem. So if you've ever like played like guessing game, you want to guess what a number is. Like you go like, oh, is the number at least 50? And then the other person goes like, no. And then it's like, is it at least 25? Yes. It's like, is it at least 37? Yes. And then like you keep asking those questions, and then you get to your answer. And what that looks in the code for these sorts of problems is like when you're doing binary search, you have like you initially start with some range where it's like, okay, I know my answer is like at least 0 and at most a trillion. And then you go like, okay, let's like check whether the answer is like at most a trillion over 2. And then based on that result, let's say like the answer is like at most a trillion over 2. Then like what we can do is like ignore all the values which are greater than a trillion over 2. And then now our highest value could be is a trillion over 2, and then the smallest value could be 0. And then we repeat that process a bunch of times. Yeah, and here's that in Python, and here's that in C++, where you generally like in your code you would write like a function which checks whether the value of the answer is at most x. And then in the example problem we just gave, this check function would contain this entire like process of like constructing a graph and then running like BFS through it. Yeah, and now for another advanced topic, so ternary search. So yeah, this is like something that's like kind of much less common in competitive programming, but still appears sometimes. And I think it's pretty cool. So the setup is like, you want to find the maximum value of a function. There's like many reasons why you want to do this. Like, as in sometimes like in machine learning, like your maximum value is like some objective function. Like I want to maximize it. Like I'm happiest at this point, and you want to find where that point is. And let's just stick to a class called like unimodal functions. Unimodal functions are like they go up and then go down. So here it goes up and then down, but then here it go like up, down, up, down. And with that, the same thing, or another way to say that is just like it has one local maximum. And then also like you need an additional property is like you can evaluate your function at x. What that means is, let's say we want to like evaluate our function at a bunch of points. You're not actually given the function. You're just given like you can evaluate it. What that means is like your algorithm doesn't actually see this curve. Your algorithm sees like the points on the curve, and then from those points it needs to figure out like where's the maximum value. So it'll naive algorithm. You look at all the points. You just go like you draw out that like curve-ish thing using only the points, and you go like, okay, maximum value is like it's one of those two things. And that would require querying all the points. Obviously, you could find the maximum that way, but it wouldn't be great. We want to like query less points. Can you use like binary search? Let's like query the middle. And then let's say we've queried the middle, and algorithm sees like the value of the function at this point is here. It's not clear what to do after that, right? Because like, is the maximum over to the right? So the function could look like that, where it's like the red. That's possible. And then our maximum would be on the right. Our function could also look like the blue, and then our maximum value would be on the left, and that's also possible. So like querying this one point doesn't actually give us much information. We can't like restrict our range by half like we did before, unfortunately. But it turns out you can make a simple modification, and then it starts working. So let's say we query 2 points. So here, there are the 2 black points here. So here, and then over here. So now we like know 2 points of information. Like, what can we gain from that? Well, it seems like not much. So like our function can still look like the blue thing. So that's still unimodal, right? It goes up and it goes down and it passes through our 2 points. That's a possibility. It could be this orange thing where it still goes up and goes down. Maximum's in the middle, and then still goes through those 2 points. But can our maximum be over to the right? Well, let's say our maximum was at the right. So what we've drawn there is that's what that red dot signifies. Like, let's say our maximum value is over there. We've already queried the 2 black points over here. Because our maximum value is on the right, it would need to be higher than both the points that we just queried. So it would have to look something like this. But then this is actually impossible. And the reason why is because, like, let's say we were trying to draw like a unimodal function. It goes up and then down, which passes through that red point and then also the 2 black points. So in order to pass through the red point and that red black point, you'd have to go like up and then down. But then it'd have to go back up again to get to the next black point at some point. So then it wouldn't be unimodal, which means that back in our original picture, like, it's not possible for the maximum to be over here. And then that's all ternary search is, like, essentially, is that now we know that maximum cannot be over here. And now that's great because now we know the answer must be over to the left. So what that means, like, in terms of complexity, is that we can always cut off, in our picture, a third of the range, because like, this part is now banned, and now we just set that as our left endpoint and that as the right endpoint, and then we continue our searching. That's why it's called ternary search, is that there's kind of 3 segments here. Yeah, and then it ends up being log of n again, because every time we're like reducing our range by some fraction. And there's actually a small detail here. So like, well, when we drew it, there was like 3 equal size sections. But actually turns out you can just query the 2 points. Instead of like making those 3 intervals the same size, you can make them any size you want. Let's say we make the middle interval like really small. And then we queried those 2 points here. And we did the same thing we just did. So now we know like the optimal maximum cannot occur over on this right side. But that means it needs to occur over on the left side, which means that we've halved the range. So now that we've like started at like a big range and like reduced it in half, so our maximum must be on the left. So it's actually back to binary search. Yeah, and essentially this is like the same sort of setup where like in an actual problem you probably won't be given like the exact problem of like find the maximum value of the function. You'll probably be given like an entire problem setup where like your goal is to like find some maximum value, and then you need to set up like the function yourself. And then let's say finding the maximum directly is hard, but you can like query the value at any point. Then you can apply this ternary search idea, except with a big caveat where like your function needs to be unimodal. So unimodal, again, it's like up and then down. You can also do it if you're trying to find the minimum and it's like going down and up. And then like over here, if your function looks like this, which is like what most functions probably look like, is that it goes up and then down, up and then down, then we can't actually use ternary search here. But oftentimes there are functions which are nice, where you can do this. Cool. And that concludes our advanced lecture. So yeah, and now you got like a small taste of like what each thing will be like, and then hopefully like the beginner and advanced lectures, you'll find something that interests you. Okay, so now we'll go towards the problem solving session. Right. Could you guys accept everybody into the group?
Yeah, so some quick logistics once we head into problem solving session. Has everybody signed up for the VJudge that's mentioned in the form? If you're not, try to make an account and join the VJudge group ASAP. Also, we have a Piazza, so if you have any questions, feel free to post it there. And another thing is, in order to access our problem sets, we require you to register an account on our mitit.org website. So if you go into the registration, and in the application form at the very end, there's an indication of whether or not you're from our class. Please write down the passphrase, I love, lowercase, everything else. Yes, it's a very, very secure passphrase. This just lets us confirm your enrollment in the class. It also gives us some basic information of your email. Try to use our MIT Kerberos email when you register. And then it just allows us to confirm, for one, to keep track of your problem submissions, and also to keep track of your enrollment website.
Wait, so this is the same website that our class website is on?
Yes.
So it should be
so it's mitit.org/registration.
Wait, Alex, should I send the
In
passphrase on the Zoom?
Yes.
Yeah, I can't see it.
I love MITIT with I-L and MITIT capitalized. I apologize for my handwriting.
MITIT is capital letters?
Yes, everything, only OVE are not capitalized, actually. Yes, compliment. After that, we'll go over some basic problems we've chosen for the binary search lecture. And we'll get to the solving parts.
Yeah, so what solving will look like, so if you, once we accept you to the group, you should be able to see these two things. You'll be looking at day 1, and then this is the VJudge website, by the way. You'll see a bunch of problems here. And I guess start with this one because just make sure that you can do the input-output, and then we'll help you with this.
Wait, when I click test one, am I supposed to see this?